We'll do what we've done the last couple days, where kind of just start on that end of the table, come around and give your perspective on what you heard today, maybe something that either caught your attention or reiterate a key point from your talk, or just the whole conference. We're at the end here, so this is your chance to talk about everyone else also.
Well, yeah, I'll just say something that I hope could see in this nice workshop, but wasn't immediately obvious to me. Is that, yeah, I was hoping we could kind of formulate kind of benchmarks, or a set of tasks for neuromorphic engineering devices and techniques. So, I mean, we have seen a lot of accelerators, Spinnaker 2, Brainscales 2, and WIHI. And I was wondering, I mean, in this lot of new neuromorphic devices, for potential users, it would help them greatly if there was a set of standard benchmarks on which we can evaluate these devices. And just beyond bragging rights on who has the best performance, I think it would also be useful as a kind of shaper of research in this area. I mean, so people coming in doing work on neuromorphic engineering, they don't get stuck with the machine learning benchmarks that have been with us for a long time. And they could begin to think in terms of problems that are more amenable to the new kind of hardware we have. This is something that I hope I could see. I don't have a good sense of benchmarks, but maybe this is something we can discuss in this panel. Because this is a problem, for example, I faced in my work, that I'm stuck with the benchmarks that are common and popular in machine learning. So if we could find something alternative that emphasizes both speed of response, power efficiency, or a kind of benchmark where online learning is key, this would go, I think, a great way into steering people towards the right kind of mindset in order to begin using the hardware and in order to think about neuromorphic engineering in general.
So agreed with the benchmark. So it is because we have this inspiration for machine learning, we're also expected to compare our algorithms to the machine learning community in general. So something I'd like to also see, I think this also reflects what was discussed yesterday or the day before, is a way of training young students into all the transdisciplinary, or this interdisciplinary field. I mean, this has been personally a difficulty of, it's possible to get very good engineering students, computer science students, in my case, cognitive science students, neuroscience students, but to have a student that knows all of these things that can be kind of productive quickly is a challenge, because there's so many things to learn about. So I think I would love to kind of push a direction in which we can have these multidisciplinary training programs and workshops. And I think to put in a plug again, so the Telluride workshops and the Cavalcante workshops are good opportunities for this, but also summer schools I think would be greatly beneficial.
Yeah, I have to agree too on the benchmarks. I think it's pretty clear that we're at a point where we really have to show that this direction is going to lead to value as opposed to always being decades out. And because there's a big difference. Obviously, I'm very excited about LOIHI, myself personally, and what seeing all kinds of talks of different types of problems that potentially we can apply the chip to. But there is a big difference between real-world problems that are being solved every day by conventional computing and the demos that we're showing here, right? I mean, honestly, I'm very excited about all these demos, and especially with, say, the ARM that Chris has demonstrated, trying to really quantify the value that the neuromorphic adaptive learning provides. And hopefully that is a starting point, and it's something that is unambiguous. But really, there's very, very few examples of that. And so I think, that's always my take home from NICE, it seems, each year, is that there's still so much work to be done, and we have a daunting challenge to really prove to conventional computing there is some real value that's going to come from this. So I think that's a challenge we all have to take on, and maybe choose some big visionary directions that we can all align around as far as benchmarks or oriented around that will demonstrate progress towards something that is an ambitious goal, as opposed to focusing on lots of smaller individual problems, which unclear how it all works together as a system to get us somewhere.
Thanks. So, I also will do the cumulative agreement with actually each of the points made about interdisciplinary training and benchmarks, and also the new devices. I've gotten a wave of optimism myself this meeting. I'm a relative newcomer, but more than before, I got a sense of convergence. A lot of the same, although we come from a real diversity of sort of source material, it's a real diversity of backgrounds. There's a lot of convergent themes on some details, some concepts that matter. And I'm also particularly happy that with the new wave of hardware, I think it's a real force multiplier to have hardware that can implement these things in the field, because there's a lot more interesting ideas out there in the world than there are in server farms. And being able to deploy things in the real world and show that real world problems with all their messiness are efficiently solvable by low power devices is like I say, a force multiplier over the things that we can just do with big machines.
So I'm going to try to be generally positive here. I agree with Mike that there's a lot to do, but as somebody who's come to this conference or this workshop 3 times now, I'm sort of staggered with the amount of progress that's been made in such a short amount of time. If you look at the hardware that's here upcoming soon, it's wildly impressive. If you look at the algorithms work that's being done, I think it's all very impressive, and I think that it's just sort of a really neat thing to see so much progress in such a short amount of time. So I'm really excited to see how that expands, into the future.
So these days, I'm thinking about and reading about reinforcement learning like all the time, and there might be some interesting first order benchmarks from that community that this community could plug the hardware that you now have into, and specifically that's OpenAI Gym. They have a bunch of interesting tasks where you have these continuous control tasks where you teach a humanoid to run, or a quadruped to run, or and a bunch of other continuous control tasks, plus all those Atari games. And if you look at the literature that's being published right now for deep RL, they're only using 2 hidden layers, and less than a couple hundred neurons in each layer. So I feel like a lot of the hardware that's been discussed it definitely has the ability to tackle these control tasks, and you just plug them in situ, and compete directly against all these other RL methods. So this is my second year here to come to NICE, and it seems like from a hardware perspective that it was maybe the first year I was just overwhelmed, but it seems like the maturity of the hardware this year was just way further along than last year. And last year I got to go to ISCA, which is the top computer architecture conference. And if you go and look at what kind of accelerators they're building, they're basically primitive compared to what you guys are building. If they do analog, they have a small matrix vector multiplier, and that's it. So it's pretty exciting to see what's coming out of this community.
Yeah, I'm actually also very excited about the OpenAI Gym, and I think this is a great way to get the next generation involved. Because the Atari framework, some of the best, RL and deep learning you can do right now is with Mario, is with Atari. And I think this is a great path to get these high school students that we absolutely need in this field within the next 5-10 years, to get them excited about it. And I think it provides a bunch of great benchmarks. One of the things that we found with what Mike's working on with the rover car is we get very similar, validation accuracies on different models. But when then we put the car in the actual track and the actual world, they perform different. And so I'd like to see some benchmark tasks where maybe these robot arms could, maybe live here at Intel on the cloud, and people could get access and actually benchmark a real arm with a bunch of stuff and, really push these tasks into the real world.
So I was also very much delighted by all the different hardware platforms and applications and theories that were presented. And I think that it's now the time for us as a community to really go beyond proof of concepts and show the neuromorphic superiority in real life tasks, and really try to get everybody in the same boat and show the world what our approach can do as a whole and not only the individual platforms.
I completely agree with that guy. That's exactly the sort of point that I tried to make at the very end of my talk, so I agree 100%. I think the thing that I appreciate the most about the NICE conference is the thing that kind of drew me to talking to people building hardware. So I'm not really a hardware guy. I'm more used to thinking about how brains function. But the thing that I love about talking to people who are worrying about the hardware is that you get to think about the problem of intelligence all the way from the physics right up to concepts. So we had people doing high-dimensional vector representations and all these kinds of things which seem more appropriate at the very psychological level. And I saw more of that here. And I think people pointing to the maturity are absolutely right that we're beginning to meld the physics and the applications in a way that they haven't been before, which is going to propel us upwards, right, to get to very large-scale systems that are able to, deal with concepts, do language processing, semantics, and all these sorts of, kinds of problems that got me into the field to start with, right? They get a lot of people into things like artificial intelligence. So, it's just super exciting, as I sort of tried to communicate at the end of my talk, that we seem to be going along that path at a speed that I think is surprising a lot of people. And I'm echoing just like a lot of the comments that were here already. And as we continue sort of over the next couple of years, if we're able to keep the kind of pace that we saw between last year and this year, it's very, very soon going to be the case that a lot of people who think of sort of deep learning and GPUs as the way that you do AI as being one of the ways that you do AI, right? And that the other one is going to really come from exactly the group inside the room. So that's what I found exciting about the conference this year, as I did last year, and I hope to see more of the same next year.
So it sounds like across all of you, mostly, you're talking about these benchmarks. But it's interesting because yesterday we talked about benchmarks, but the panel was a bunch of neuroscientists. Today, there are a couple of neuroscientists on the panel, but for the most part, it's hardware and more machine learning that's represented. And the tone was very different. I noticed that at least. Because yesterday people were talking about intuition and imagination and very high-level cognitive tasks that could be used as benchmarks. But here we're hearing OpenAI Gym, something that's very practical and accessible to the computer science community today. So I guess the question is, what is the 2-year goal? Like, if let's say next NICE we had a challenge that said, we introduce, a challenge that says, okay, we're going to solve this OpenAI, play Mario in spikes, or we're going to fly a drone in spikes, or let's say a year from now we set a challenge that in 2 years we could have a very clear competition on where we look at power and accuracy and so forth. What do you think? Who has an idea of what that could be that maybe would be exciting both for us as well as for the outside community?
So I like the physical robotic arm challenge, but perhaps what could be started with, there's an open source physics simulator called PyBullet, and people are doing robotic simulations with it. And perhaps there could be like a tiered challenge. This is based on a conversation I was having with Craig Vineyard. There could be a tiered challenge where initially people competed on the simulated robotic arm, and so you would want the simulation to mimic a robotic arm you could actually eventually access. And the winners of the tiered challenge could then get access to a physical robotic arm and compete on some sort of robotic arm task.
I'm not sure what the challenge should be, but I think there needs to be a clear delineation if we're talking about hardware or algorithms. Maybe it seems like maybe a decoupled challenge is there, but I do really like the idea of NICE holding some sort of challenge like what we're talking about in terms of benchmark tasks.
I'd like implemented hardware for an artificial nose of general application that isn't terrible.
Okay, let's do that. Yeah, I think robotics long-term seems to be one of the main, if not the killer app for neuromorphic computing. That's, after all, what brains evolved to do. So, a challenge that comes to mind, really that seems top of the list, is to really embody these things and show what they can do in whatever scale being.
So in my lab and also my colleague Jeff Krishmar, we got interested into this human brain project neurorobotics platform, which I think is really nice. It's basically a community of these virtual robot platforms, robotic platforms for testing ideas, connecting it with your own simulator and hardware. And I think the real strength there is that you can build a robotic platform and share it with the community, and they themselves can actually come in and test their own algorithms on it. So, and there's a lot of momentum behind the human brain projects right now. So I think that neurorobotics is really one direction to go to. And I think it is also compatible with the desire of doing reinforcement learning and cognitive agents, basically learning in new environments.
Well, yeah, I'll just add, I think robotics is a task where you get a tactile, physical feedback on how good you're doing. I don't think I have a clear task in mind. It's just a set of features this task would have. I think it should weed out conventional approaches that we have until now, for example, in machine learning. And it should really emphasize power constraints so that we kind of have to make use of novel hardware and not depend, for example, on using GPUs. And probably should also include some form of learning online where the agent goes into an unexpected environment and has to respond intelligently and learn from its mistakes. So in general, yeah, it should be a task where current conventional approaches aren't gonna cut it. And yeah, just encourage thinking out of the box along the directions of using novel hardware and the neuromorphic mindset, basically.
So I should say that anyone in the audience have an idea on this thought? Karl-Heinz.
Yeah, I think we tend to think that a natural environment is the environment to do neuromorphic computing on because the brain has been evolved to do just that. And of course, I agree. It's an obvious choice. I must say that my dream of using neuromorphic systems was always to do more analysis of also more abstract data, and in particular to do abstraction from spatial temporal data streams. Let me give you an example. There is a lot of spatial temporal data that is not recorded by human beings or robots. There is, for example, if you looked at the weather of the world, there are lots of sensors that are all around the world that have spatial patterns of temperature and pressure and wind flow, and also they develop as a function of time. And there's a lot of underlying physics there, which in principle is known, but in practice, of course, is very complex. So to build an intelligent system that is able to analyze the temporal evolution of weather on the world, discover the rules, and then make predictions, that to me would be a very interesting challenge, because there is a very big database available that is easy to use, and then to rediscover the laws of thermodynamics and use them for predictions, to me would be a real big success.
Yeah, I think that would be tremendous, especially if you could have this thing watch the weather for a while, and then does it discover the concept of hurricane or tornado or El Nino? And if you could sort of find those at the higher level nodes and it sort of on its own built that as a concept and then maybe use that concept in its predictive model, I think that would be tremendous.
I was wondering whether there's any benchmark that kind of would classify the model or hardware as actually being intelligent. So a lot of the benchmarks are kind of doable with models we have right now, but the question is more, do we implement them in spiking networks or more efficiently? But can we go like context aware or a higher abstraction level? Would there be a straightforward benchmark for that? I don't know.
So you want to benchmark the intelligence somehow?
Yeah, so one of the questions is, I mean, right now the typical benchmarks, the MNIST or CIFAR or something like that, they work fairly well with a certain class, whatever you train it on. But as examples, the other day was shown, if you take pictures to a different context, those networks usually don't really work that well. So having this higher level of abstraction that without a lot of retraining, that you still can make good predictions, which would probably be closer to actual intelligence, I guess.
So I think what you're referring to is a kind of transfer learning, which could be exploited by comparing playing Mario and then playing Sonic.
But without a whole lot of transfer learning. So really with very minimal, like people do, the transfer is usually a very quick process. As far as I'm just an amateur, but as far as I'm aware, right now transfer learning really implies quite a bit of extra learning in the transfer process. So, relatively speaking, so I don't know if that's if there's something that would be an easy benchmark for that. I don't know.
Yeah, so I don't know of any. Do you?
So I don't know of any easy data sets for that. But I will say that one thing, if we're looking for this goal of having a nice benchmark task, I think one of the real benefits of the benchmarks that the deep learning community has had, and one of the reasons why they had so much success, is they have very well-defined problems and really well-defined metrics for those. So some of these problems are really difficult to say, like how well something transfer learns or how well it adapts to new contexts. And so I think we should do some real thinking about how we can measure that quantitatively so we can compare. And I think it is important to compare against existing models in reinforcement learning or deep learning so that people can have a good context in terms of comparison with whatever amazing AI solution we come up with, right?
So I'm not the world's expert in benchmarking, but it might be my impression at this point is that we're not going to be able to get sets of standard benchmarks like you use to compare algorithms on common CPU platforms. We've seen that the success of neuromorphic algorithms and spiking ones in particular is really dependent on the task. Of course, there's also individual algorithms involved, but I suspect that the benchmarks are going to have to be about the tasks themselves because they'll differ tremendously based on the nature of those tasks. And so you'll end up with a family of benchmarks which apply to a greater or lesser extent to anything you intend to do. And obviously,
to be fair, they do that for traditional CPUs also, right?
Yeah, I said I wasn't the expert, right?
Sorry.
So
I was just saying, to be fair, they do that for traditional CPUs, right? You benchmark on Cinebench or any of these like benchmarks, like LOPAC or Graph 500 sort of tasks. So, and I think,
more so, I think.
But I mean, I agree overall, right? That is what we do. I think the one thing that's really exciting about this meeting is, not everybody's sort of obsessed with the classification accuracy, that things like power and time are really going to matter. And when we have a benchmark, we're really going to have like 3 columns. What was your accuracy, what was your power, and how long did it take?
So one comment here is, I think the human in the loop is an important part of any benchmark rather than just task, right? So a family of benchmarks you should consider is like how long can you keep, Alexa has been putting it out, for example, a conversation, right? Can you sustain a conversation for 10 minutes with human subjects? So things like that are a little bit, they are variable, real life, like, it's equivalent to putting it out in the open, but also quantifiable. And also, it is about, and I think by being aware and participating in those challenges, I think it's a similarity with the games. Gaming is not about the rules of the game, it's about the human interaction. And I think that's really part of it, right? The human in the loop should be part of the benchmarking. And then I think you can really show off maybe some of the advantages better.
So I think that's a great idea. But I will say that I think we lose something if we ignore situations that are human independent, like predicting weather, for instance, or
no, I'm just saying one class of it. I'm not saying that should be the only one, but surely I think that is a possibility for really doing more end-to-end, and then maybe it'll help you think about how to set up all the layers to define a full solution.
Right. And I also think there is a practical problem of how one researcher collects data that involves interacting with humans. Like, that's an expensive process. You have to bring people in or survey them on the internet or something like this. So if there's some way we can have a collaborative effort so that we increase the accessibility to those sorts of experiments and tests and benchmarks, then I think that would be something that the whole community could really benefit from, because it's really hard to do that sort of thing. But if there's some way that you can do, particularly in a semi-automated way, where a researcher at any university could tap into these human experimental interactions, then that would be great. I mean, it's hard because you have all these approvals and whatnot you have to go through, but that's a hurdle that you have to do, and I think it's a really nice idea to have a human sort of push back against the computer system.
Yeah, I think from industry point of view, benchmark is important, but benchmark seems to be more or less focused on the competitors and what the Intel is doing, what the Qualcomm is doing, what TSMC is doing, and where we are compared to the current status. Right now, I think two things are missing. One, what's the roadmap? In the semiconductor from our own field, we have been driven by the roadmap. And the roadmap for 65 nanometer, 7 nanometer, 5 nanometer. Yes, right now it's come to the end. It's very straightforward. And everybody, all the university, academia, industry, everybody was moving in that direction. There's a roadmap. Right now in this society, I don't see a roadmap yet. And whatever benchmark we are talking about is the current people are doing. Software guys are doing the deep learning. Hardware guys are trying to catch up, and software guys say, forget it. You cannot catch up with us. Yes, they are competing, but yet, what's the future? What's the 5 years from now on? What's 10 years from now on? 15 years, or 20 years? What is bio-inspired computational element roadmap located, where each of us is supposed to position ourselves? I think those are open questions, at least from our point of view, seems to be also important. Benchmark is important, roadmap is important. Where is your position? I think these three things may need to be answered or addressed as well.
So I'll chime in real quick. With miniaturization of transistors given Moore's law, it was clear what the goal was for 70 years, So, and maybe it wasn't 65 nanometers, maybe it was 63 nanometers, you discussed that. No one can define intelligence. We can all make up a different definition. So I guess before you even have a roadmap, where is the road going?
That's very important, yes. I think yesterday last night when we discussed during the dinner, currently there's two trends. I see there's two routes as well. One is accelerators. Everybody is trying to competing with each other in terms of the performance, the energy efficient and cost. So that's the AI, they call the technology for AI. And it's moving to that directions, and it's you cannot stop it. On the other hand, there's a lot of brain-inspired, which make everything smarter and adaptive, and like Loihi or whatever. But you cannot compare this one with the accelerator. And where this is supposed to be in the position, to my view, is future. Maybe 10 years from now on, it will be really smart. It will overtaking the position what the accelerator right now is doing. But that's the goal. We position ourselves in the future, not immediate. Some people who are working in today's community, I would think is closer to the current situation. It's 5 years from now on. But yesterday's group, maybe 15 years, 20 years from now on, and make everything smart and make artificial intelligence really viable in a way that we like to. But some community like us probably need to think about how to define, or if it's possible to define in the different directions for the AI technologies or whatever you can think of.
So any thoughts from the 5-year outlook folks?
Yes.
I think that road has a lot of fan out. As you're saying, that if everyone has a different definition of intelligence, then those are going to be maybe different projects. And there's some ideas that you might need special hardware and special application software to solve each of these different problems. So if we think of intelligence as sort of a suitcase of all these different problems, we might have to address them individually first.
So I think that points out one of the major risks in the field, which is that progress may not be iterative and incremental like it is with miniaturization of process technologies. It could be bursty and unpredictable. And the risk as I see it is as we move from kind of a soup of neurons towards something that's bio-inspired, that has specialized neurons, specialized circuits, specialized regions of the brain. As we try to reproduce that, you may not be able to do one at a time and see incremental improvements to what you're seeing, to the performance. It may be, like building an arch out of bricks. It's not until you place the last brick that it's able to support itself. So do you see it as a risk that we have this kind of bursty, unpredictable, complex interconnection of these different techniques that may not prove beneficial until we put them all together? And how would we mitigate that risk if you think it exists?
I think it's definitely an issue with systems design in general, because if you optimize one component, you often break the whole system.
So, I mean, I'll agree wholeheartedly that, it may not make any sense until it's finished, and it could be worse than current, like state-of-the-art, until it is better, right? Because you don't really know sort of what that landscape looks like. You could be stuck at a local minimum. You need a completely revolutionary thing to sort of pop out of it to do better eventually, right? I don't think it's inherently bad that that's how research goes. It's just the name of the game. You got to stick with it, have some intuition and some hope, I think. So,
I do feel the need for benchmarks, and in a sense, I believe that although we are from academia meeting with industry people, both industry and academia should serve society. If they don't serve, they should be washed away. In that sense, in analogy to the real estate logo is, location, location, location. The question about benchmarks will always be ill-defined if we do not define the need. So what is a need that we are covering? So a need can either be addressed or imposed. An example of an imposed need is this. We're all carrying these huge screens that are potentially dangerous for our life. right? I mean, potentially. I mean, I'm not saying anything more than that. We're all doing it because that need has been imposed to us in a way that supports a fundamental thing for ourselves, communication. And I believe that there is a need that can be addressed by a neuromorphic community that has not been touched yet and has not been addressed even by a single talk. And that need is, look, all of us, sooner or later, one of us or all of us will face a problem with our health. That need is something that has been before us and it will stay after us. So we have a really interesting tool, the neuromorphic, something that imitates function, and we're not using it to treat diseases. I don't know if that raises any eyebrows or seems like a heretic voice. All I'm saying is that this need is there, and it's not me that I'm going to impose it. We're all going to be healthy.
So I will say the Human Brain Project folks, brain scales
Yes,
and Spinnaker.
I agree. I'm more in the, from the US perspective, although European, but I agree. Yeah, I agree.
So I'm going to go a little bit off topic, Konstantin, then come back to what you just brought up. So on the benchmarking topic, if we look at the CNN community, you know, that phrase CNN community has meaning to us when I say it because of image competitions. You know, they were making, what was it, 0.5% per year in improvement before CNNs were introduced, and then it was a 12+ % improvement that year. And so my point is that, you know, this community, however we, you know, design the benchmark, like that's where we're headed. Like that, this whole CNN community is optimizing for performance on images or related tasks. They're fanning out too, but they're optimizing performance on their benchmark. So we will head towards and make contributions toward whatever benchmark we pick. So we need to pick, if we pick fun benchmarks, then we'll be making, you know, doing that. But if we pick health benchmarks, then we'll be headed in that direction, and so on.
I'm not sorry for perhaps misusing the opportunity to speak twice. I'm not saying that robotics is, for example, a great opportunity for neuromorphic. When I'm doing this, just this one, my brain controls 200 degrees of freedom in this, at the moment that I'm doing it. If you look at the robotic soccer tournament, you find all these rigid bodies, and you can look at YouTube videos and you'll see how unnatural they are. And this is not a problem of engineering. Engineers did really good job. It's a problem of scientific foundations. There is no knowledge that can be translated from how the brain works to robotics. And this is something that I believe neuromorphic computing can actually contribute. So I'm not saying that it's only health. I'm just giving a perspective that I didn't hear, at least in this.
Okay.
I'd just like to say that I believe benchmarking is a bit of a red herring. It helps us make progress. I don't want to denigrate it completely, but it provides a focus to go and build the best system that can get another, 12.5% on CFAR. So one of the phrases that's used for what we're doing is artificial general intelligence. And I think we should be building a system or a much smaller set of systems that are not tuned to a particular domain, but can cross domains, may have to relearn, may have to transfer learning. But it's not a whole lot of systems all in different areas. It's like the PC when it came out. you could use it for your checkbook, you could use it to write email, you could use it to write blogs, all sorts of things, all on the same machine. And I think that's a better paradigm than trying to address any individual domain.
So to maybe rephrase what you're saying, this community is still probably in the explore, should be in the explore stage, as opposed to the exploit stage, because we're just getting our feet on the ground.
So, I mean, maybe the most general thing we can do is it's sort of on the horizon, and we have Alexa and everything, and that's personal assistance, and maybe even robotics for care of the elderly or infirm or whatever. But that sort of application that requires a broad range of activities, but has some impact on the community.
Mike?
Yeah, I think what I heard you say is something that does resonate and is something I've been trying to articulate inside Intel when I try to describe the value that we see in this domain. And that's the generality of potential applications that it enables. So it's not just that we'll be able to do some incremental improvement on some standard benchmark, do better cat recognition or something. It's just the broad range of varied algorithms and problems that this same computing substrate can solve. And right now, when I try to give that argument, it's well, we have very minimal results today, but this is the vision. We see this in all these different directions. But it'd be great, when we actually have some capabilities, and then I think that breadth argument is very, very strong. So I do feel, I guess I'm in both camps. I mean, I certainly feel that we need to quantify the progress we make, because we have to be very clear about, we're not hiding certain aspects, we're not, not counting all power consumption aspects of the system. It has to be very clear and unambiguous that there is some value that's being created. But absolutely, that breadth argument, I think, is really powerful.
Okay, so I think I totally agree with every point that people make about benchmark today. But I want to, because I'm an algorithm person, I'm not a hardware person, and I come from neuroscience. I spent maybe half of my enlightened years recording spikes, and another half putting up artificial systems, spiking systems, trying to do something. Well, my view is our understanding is still not sufficient. So I think, for a benchmark, let's take deep learning. We're talking about Imagenet. So what is Imagenet competition is really about a solution. And it really doesn't care about how you reach at this solution. It may require you 1,000 GPUs training for 2 months. Well, if it's what it takes, and you win the top prize, you still win the top prize. So this kind of challenge just decouples algorithm with hardware. And look at today, there's a big competition in the hardware realm for accelerating deep learning. And this is really another fair competition because, again, we know exactly what exact algorithm we want to accelerate. But we're not at that step right now. I think for especially for spiking networks, because there are 2 feet. I think the hardware feet is maybe 3 feet ahead of the algorithm feet. Shame on me, because I'm an algorithm guy. And I don't know if this kind of pessimistic view is really shared by a lot of people, but I think we really start to see a lot of things for example, spiking LCA. So we need to really identify such cases where, and maybe host competitions, where spiking solutions really shine, not just because of hardware. So it is easy to make lemonade from a lemon when you have a lemon, but it's just not fair if you have an apple because there's not much juice in it, right? So that's my point.
Karl-Heinz?
Yeah, I just want to bring the discussion maybe also towards a point which maybe not be so popular, which, there is a benchmark, probably the best known benchmark in computing is the Lindbeck benchmark for supercomputers. And although many people say that's kind of stupid because it doesn't really measure the kind of performance that is relevant for real-world problems, it has still driven the development of that field enormously. It has always been the motivation to pay for the next generation of supercomputers. And I mean, there are also similar technical benchmarks for neuromorphic computers, and I think we should also consider them very seriously. If we write our applications to funding agencies, at least if I do that, I always point to the three big advantages of brain-inspired computers, is that they are energy efficient, they are fault tolerant, and they have the ability to learn and to self-organize. And that is what normal computers don't have. And I think we definitely have to show these features, which represent something like, I think the word superiority was mentioned in the initial round of this discussion. And the quantum computing people, they always talk about superiority of quantum computers in certain aspects. So what are the areas of superiority of neuromorphic systems? In fact, it is, of course, energy to solve a given problem. And one of the benchmarks, I think, at some point has to be that we all agree on a problem. I mean, whether it's an interesting one or not, I don't really care, although it should be interesting, of course. And then we just measure the energy it takes to solve it. And we compare that energy. That would be a very relevant benchmark. And we also compare that to conventional computing approaches. The other one is fault tolerance, which we almost never discuss. But I think it's a key. I mean, our own brain, we use a cell per second. This is what I learned from the neuroscientist. We lose 100,000 cells of our brain per day. And our systems, if they are designed correctly, should also have this kind of fault tolerance. And that is a very relevant quantity, in particular when it comes to using novel devices at some point, like nano devices, which inherently will be very unreliable. Can we demonstrate that the systems we build really have this feature of fault tolerance? That also can be measured quantitatively. You can say, my system still has a performance of such and such, even if I switch on 50% of the synaptic connections. Maybe exaggerating a little bit, but I mean, that kind of benchmark would be an important one. And thirdly, and most importantly, of course, is the ability to learn. Clearly, and the question is, what are the resources you need to learn? I think we had a very impressive talk here by Wolfgang Maass earlier in this conference, where he showed a concept that he calls L2L, learning to learn. So he evolves architectures that have the ability to learn and that also in a way optimize the resources so that you have a learning system that in an optimum way uses neural resources. Yeah, so what is a system that can learn, uses minimal resources, and can learn a certain category of tasks? That is also something normal computers cannot do, and it could be a benchmark, like we give a category of tasks, what is the system you can offer that is able to learn with a certain number of given resources? So these three aspects, fault tolerance, energy efficiency, and ability to learn, I think can be measured and have to be measured and can be compared to conventional computing approaches.
Can I, before you walk away, I want to clarify something. So LINPACK is a hardware benchmark or architecture benchmark. It's not an algorithm benchmark. If you read the fine print, they say
okay, but it's
you
a benchmark.
cannot use Strassen algorithms for LINPACK.
I agree. But it's a benchmark. It puts a mark in the bench and it measures how good your system is.
But when you look at neuromorphic computing, you can build hardware and you can quantify the energy per spike event. But the algorithms
not per spike,
are co-evolving
really to solve
with the
a problem. I mean, a spike is something, it's an interesting unit, but I think we should measure the energy for a given problem or for a given category of problems. Really solving the entire thing, probably also including the learning phase.
So it would be an algorithm to architecture to hardware implementation combined.
Yeah, solve a problem and tell us how much you pay for it in terms of energy.
Any thoughts on that challenge?
It might be interesting to have a fixed budget of energy and then see how much of the problem people could solve.
Yeah.
So I have something to say. So maybe you don't have benchmark because you don't really need them right now. I mean, maybe it's not popular point, like maybe it's not popular position right here because everyone's saying, oh, we need benchmarks. Guys, I think you don't really need benchmarks because there are so many troubles with benchmarking generally. And right now, like when you need benchmark, when you have multiple choices, when you have many similar things fitting in the same, like providing you the same set of tools, and you don't know which one to choose for your particular task. Right now, we have very few things, right? And we have like many very different tasks. So like couple of years, like 16, 17, my group, we were doing some storages, and people in there really suffering because of absence right benchmarks first. So sometimes on our panels, we also see the same discussion. And also, when you can't win benchmark, bring your own is working in the storage industry. So there are very big number of benchmarks, all just beneficial to some particular tools because every tool is still a bit different, right? And it's never bring you anything. And it's a substitution. When you're quantifying the success or quantifying the progress, it has nothing to do with benchmark. And also, benchmark generally means that there are some kind of predefined conditions or data or something like workload, right? And it's also a really great substitution. I mean, bringing yourself from possibilities to define that data, just use something what not defined by you but someone else, and it may be just pointless or even, I mean, dangerous in some sense.
So you're basically saying that benchmarks are risky because a bad benchmark can cause more problems than
they just risking because they actually bring +1 variable in a complicated equation of what we are doing, and maybe they bring their own impact on some decisions or some development or strategies. And right now in here, we do not have troubles in choosing right neural chip for task, right? I mean, they're very different, so we generally don't need. And actually, how you put your topology on a chip, this is really more important rather than, let's say, picking up chips. So, and also, they're so different we can't compare them. I mean, in terms we're talking about hardware, right? So, but you can benchmark anything, literally. Yes,
So to the panel, you know, engineers like to have goalposts to go for, but do we actually need them right now? What are your thoughts?
We don't know what the goal is.
Yeah, I think it's just like many other aspects of engineering, it has to be very carefully considered. I mean, that's why I push back a little bit on just fixating on synaptic op energy, because that's just way too minuscule and small a number to focus on at this stage when the feature set is not even clear what you need, and that's going to have a big impact on the synaptic op. So it will drive optimization in the wrong way if that's, you know, the only thing you're focused on. At the same time, you know, if we take the Turing test as our benchmark, well, that's not very interesting or useful either, because that's just going to be one answer for the next several decades, and you know. So it just has to be carefully considered and engineered itself, you know. But I think we need them. I think it's obvious.
So completely agreed, except with one caveat. I think that this little conversation program on the TRS-80 in 1978, I think passed the Turing test for many, many people. What was it called? ELIZA, I think.
All right, got a question here.
Yeah, so I would like just to share Mike's comments and others that I think really we need to solve the breadth of the problem instead of getting lost in the benchmark. So I would like to share a real life example that I encountered. So like a few of my neighbors, like they didn't pass the high school even because of financial constraint. So they always talk with me like I'm an algorithmic person, that's what I'm doing. So I tell them the problem that I'm trying to solve as well as the results I'm getting. I'm saying that, okay, I'm improving 5% improvement, 6% improvement. Okay, so they listen every day and leave. And then actually when the TensorFlow came, the deep learning became pretty good. So they actually have a problem in their backyard is they have an animal intrusion problem. So in their backyard, they have regular animal visits and they destroy their landscape. And so so they always kind of ask me, can you have a solution that I can use and all? So when the TensorFlow and deep learning came, so I kind of show them how they will collect data, how actually they can develop a model very quickly, so that when any animal visits them, the sprinkler will be turned on. But when their kids are playing, nothing will happen. And they took that advice, and the framework is that powerful. They did their own programming, and they developed a solution, and they taught now to so many kids, to their community, that they really showed the power of machine learning and deep learning, what in my life doing all these benchmarking and all I couldn't achieve. So we really need to focus on real problem solving, which increases the power of humanity, that I believe. Thank you.
So that gets to the accessibility that I think William talked about, that people, who cares what the benchmarks look like if people can't use the technology?
Yes.
Just one quick comment. Well, Sam mentioned, OpenAI Jim. Well, they have a very wide array of benchmarks. They have tons of them, and they kind of aggregate them all into one sort of, what's that athletic event where they do a bunch of different things? Well,
Triathlon.
I mean, like one person does, like in series, does a bunch. They got triathlon kind of thing. I think a benchmark triathlon that hits on all the right general abilities, that you have to throw one architecture at it that has to do all of them. And you can't, you don't get a pit stop or to retrain it or retool it in the middle. Something like that seems like it would be okay. And I think that that's sort of what they're going for with OpenAI Jim. That's why they spend so much time, building such a wide array of benchmarks, that are individually maybe not that difficult to fine-tune a system for, but collectively present a real challenge. So it's just my 2 cents.
So we're getting a little towards the end here. Let's have an opportunity if anyone wants to have something to say that's not about benchmarks for a few minutes. It was inspiring conversation, so.
Maybe just a comment about the sprinkler project. I think it's fantastic this is getting out into the community. I think it's nothing less than an emergency. These technologies are extremely powerful, and if they're limited to just a few groups, I think that's dangerous. I think we want to have this, widespread knowledge. We need to do that now. We can't wait and do that in 15 years from now. It'll be all wrapped up.
My name is Dan. I'm from Samsung. And then it was a really kind of a great chance for me to hear about the neuromorphic kind of computing system, actually. My major is in material science, not a computer science, and then not a neuroscience or something like that. But the question I have is going to be about the, second day, I forgot his name, but someone mentioned about the some kind of neuromorphic computing system have one of the major problem is memory, actually. So, I'm kind of Samsung, so this is why I kind of ask you about the kind of memory side in the computing system, actually. So, after that point, I hope that somebody mentioned about there was a problem, speed problem, or capacity problem, or, what is the problem? I hope that someone mentioned about that, actually. So, if anybody know that the answer for that, can you please help me to find the answer? And then the second question I have is going to be about the, for example, TikTok game, right? So we play the game, and then computer is going to be smarter and smarter, and then, eventually it's going to be better than human being, actually, right? But if we turn off the computer, it's going to go back to the first stage or whatever, right? So then, which means that, someone may think that about the non-volatile memory or something like that, right? So, do you have any kind of a answer about the kind of a non-volatile memory or power or something like that? My third question I have is about I was shocked, actually. So when I go to the demo, actually, right? Except for the engineer who set up the demo, nobody used the keyboard and mouse, right? So everybody use the kind of an image sensor or kind of a sensor, right? So maybe 5-10 years later, I mean, how do you think about the sensor market area, actually? I mean, computing part, yeah, right, definitely everybody working on that. I mean, it's going to be, it's going to be there, actually, right? I expect that. But, you know, what about the sensor part? Have you ever think about that? So, I mean, I hope that the...
I can comment on the memory technology.
Yeah, please.
Well, so certainly that's probably the most critical circuit element in neuromorphic chips. I mean, neuromorphic computing is logic and memory intertwined. You know, that's one of the central properties inspired from the brain. But on the other hand, I think, you know, just like, say, fixating too much on optimizing synaptic energy now, focusing too much on driving to the next memory technology that's perfectly adapted for neuromorphic computing, that's also a little bit early. Obviously, it's much longer lead type of research, so it's great that there are people out there exploring all these exotic new devices and ways for doing memory, but I think the problem today is just to get the basic algorithms, the computational model, the architecture right, and for that, that's, you know, I believe CMOS, digital, that's just the way to go for the, you know, just those simple benefits that we can actually make quick progress that way.
So then you don't see that there any kind of a speed issue between the kind of a logic area and the memory area?
Oh, there's no speed issue, certainly. I mean we use SRAM because SRAM is the fastest.
Yeah, I know,
you know,
but
the
yeah, what about the, you know, but SRAM is not good enough to store all the information from the bunch of neuron, right?
For now, there's a great thing called a hard drive that we can just put everything
Oh, you think that, so currently you use the hard drive actually for that?
SSD.
Oh, okay,
I
SSD,
mean, just
okay.
that's not the most pressing problem, right, to allow the chip to boot right back up. For some applications, that would be relevant, but again, this is just maybe a decade out or something when that becomes the you know, there's always a priority list, right?
I see.
As far as I see it.
I see.
Okay, so let me, it's 5:30. I think the agenda said we were going to end around 5:15, actually. So I want to finish with one very last question for everyone. Just should only be like 3 words each. Coming down, how long until every American or every person in the world owns a neuromorphic chip, either on their cell phone, self-driving car, whatever? How long until this technology exists in 5 billion people's hands? You just say 10 years, 50 years, never.
I don't know. That's a simple answer.
I'm going to have to answer a little bit longer. And this is what I had in general, is that how many people actually benefit from deep learning today in their everyday lives? Personally, 0. It's annoying to me. It's, you know, it's everywhere. I do use Google. In fact, Google Images is probably the only place where I find it remotely useful. And searches to some extent, yes, I agree. And that's exactly why I find it annoying. So a few examples apart, I mean, what drives what people really, the hype of deep learning is not what is affecting us every day. So when you say, so how long until people have neuromorphic chips? I mean, the question even is now, how long until, you know, people use what the existing technology, AI technology like we have today? I mean, they don't even have it now. So
it's fair. Mike?
I think the latest Apple chip does have deep learning in it, right? An accelerator for that. So probably today it would qualify that most, maybe half of the population has it in their cell phone. Yeah, so I would have to go with something like 10 years. Maybe a little longer, maybe a little shorter, depending on just how things go. But that, because you pretty high bar, everybody to have it.
Yeah, so for everybody, I think you're asking me a question about poverty, which I'm not sure we're qualified to answer.
Yeah, I don't want to get into sociological things.
Yeah, well, you know, I'm halfway there. So, but in terms of the number of people, among the people who carry cell phones in their pockets right now, I expect equivalent devices in the 10 to 20 year time frame will have some small neuromorphic-ish chip doing what it does best as a coprocessor.
Yeah, so if that's the benchmark, or bad word. If that's the the metric, right, is that everybody who has a cell phone has a neuromorphic processor, I would estimate probably in the 15-year to 20-year range. If it's everybody, that's really unfair to a large portion of the world. So.
Yeah, I don't know. I think I'm inclined more towards Mike's estimate of 10 years. I think 10 years. Anybody who wants a phone will be able to have a phone.
It does depend on your definition of neuromorphic also.
Yeah, Lloyd
but
Watts,
in 10 years.
Lloyd Watts would say everyone has one now.
For instance, yeah.
But I think we're talking about these more general purpose neuromorphic processors like Louis and so forth.
Yeah, I'm more of the opinion that we kind of have a lot of this stuff now. You know, if you go back to 85 or something and you sort of ask them, they would say that we all use AI every day now. I think it's kind of interesting if you asked people on the street how many transistors they had in their pocket. I mean, they'd be like, what? So I don't think it'll ever be sort of a conscious thing for most people. They'll have applications that they enjoy using, but they might not ever really be aware that these things are here.
How many years until Louis in your cell phone?
I think less than 5. I mean, it depends. You know, like I said, I think it's closer to here now.
Just in the software.
In the year 2025.
7 years, very specific.
I want to say that I think there's going to be interesting commercial applications within 5 years, and then widespread, maybe 10. So there's my guess.
Thank you. All right. With that, I think that we should probably call it quits. Thank you all for staying through the whole meeting. That's a round of applause for the panel here.